Okay. Hello, and welcome to another wonderful adventures of the New York City Category Theory Seminar. It's April 6, 2022. I think this is going to be our 51st taped series. Anyways, and tonight we have the pleasure of listening to Jason Parker talking about enriched structure semantics, adjunctions, and the monad theory equivalence for subcategories of arities. Take it away, Jason.
Great. So thank you so much for having me. So to kind of answer that list of questions, so I think, right, so I was born in Ottawa, Ontario, Canada. That's the capital of Canada, of course. And I did my undergraduate degree at Queen's University in Kingston, Ontario, Canada. Then I went to do my master's actually first at Carnegie Mellon in the USA. And then I came back to Canada to do my PhD at the University of Ottawa. And I'm currently a postdoctoral fellow at a small university called Brandon University in a small city called Brandon in Manitoba, Canada, as I've written here. Right. So I think that was all the questions.
It was something else before it was Brandon University. No, wasn't it something else?
No. So I went straight from my PhD at university.
No. I mean the name of the university, Brandon University. Was it something? Well, maybe.
No. That's the name of the university. Yeah.
Okay. Sorry. Okay.
Yeah. Sure. Sure.
Fire
Thanks.
away.
Yes, this is enriched structure semantics adjunctions and monad theory equivalences for subcategories of arities. It's joint work with my postdoctoral mentor, Rory Lucyshyn-Wright at Brandon University. So thank you again for having me. So this talk will be somewhat, well, yeah, so I guess it's largely based in enriched category theory with applications to some diverse areas of mathematics. But so hopefully it won't be too heavy on the enriched category theory, but I think that the examples that I will give will hopefully help connect it to two different areas of math. Okay, but so having said that, I will dive in. Whoops, okay. Just to motivate what I'm going to be talking about. So as most of us or all of us probably know, so there have been several structure semantics adjunctions and monad theory equivalences established throughout the history of category theory. So probably the first one was established by Lawvere, as we were just talking about. So I think in his PhD thesis, that's the 7 here, he established a structure semantics adjunction between Lawvere theories. Those are the objects on the structure side of the picture, and what we now call tractable set-valued functors. So there's certain functors going into set that are nice in a certain sense. Those are the objects on the semantics side of the picture. And then later, actually, Linton generalized this adjunction to a more general context. And then in the context of enriched category theory, so for a complete and well-powered symmetric monoidal closed category V, Dubuc proved in this reference, I think this is Dubuc's textbook. So he proved a structure semantics adjunction between what he called V-theories on the structure side, and then tractable V-valued V-functors. So tractable V-functors into the base of enrichment V on the semantics side.
So does that thing with the V's generalize Lawvere's thing, or is it just analogous to it?
So here, right, so with Lawvere's thing, so V is set, and so Dubuc's result doesn't actually quite generalize Lawvere's, strictly speaking, because so these V theories are not or don't generalize Lawvere theories. But on the next slide, I will mention a certain result that does indeed generalize Lawvere's results here. So yeah. Okay, so in the same reference as before, so Linton showed that there is an equivalence between Lawvere theories and finitary monads on set, the category of sets and functions. Now, then John Power in, I think, 1999, in this paper, he generalized this equivalence of Linton, which from the base of enrichment set to an arbitrary, locally finitely presentable closed category V. So basically Power showed that if you take any locally finitely presentable closed category V, you can get an equivalence between certain enriched Lawvere theories and enriched finitary monads on V. So then, quite recently in 2016, Lucyshyn-Wright then generalized both of these results of Linton and Power by showing in a quite general setting that if you have what he calls an eleutheric system of arities J in a symmetric monoidal closed category V, then you get an equivalence between these so-called J theories, they're an enriched notion of Lawvere theory, and what he calls J airy V monads on V. And okay.
What is the word LU?
Yeah, so that's I'll define later. So yeah, just but basically it means essentially that V is a free co-completion of J under a certain class of colimits. I'll give the exact definition soon, but yeah.
I'm just wondering the etymology.
Oh okay. Yeah, sure. Yeah, good question. So I believe it's, so I think he actually says this in the paper 10 here. I think it's, so apparently the Greek word for free is eleutheros, I think. So I guess he kind of coined the term from that, that Greek root. But yes, so basically I guess like, so eleutheric is supposed to have the connotation of free or being free because being eleutheric or J being eleutheric basically means that V is a free co-completion of J under a certain class of colimits. But yeah, I'll give the precise definition later on in the talk.
Okay, perfect.
Okay. So, right, so that was in 2016. Then, even more recently, in 2019, Bourke and Garner, so John Bourke and Richard Garner, building on, I think, 2009 paper of John Power and Nishizawa. So Bourke and Garner showed that if you have any small subcategory of arities J in a locally presentable V category C over a locally presentable closed category V, then you obtain an equivalence between J theory, so again, a certain kind of enriched Lawvere theory, which is in some sense dependent on J, and what they call J nervous V monads on C. So I'll define almost all of these terms quite soon, but hopefully this is not sounding too kind of unfamiliar or strange, but yes, so this was a quite recent result by Bourke and Garner in this paper here. Okay, so now the point of all of this background is that, so these monad theory equivalences of Lucyshyn-Wright and Bourke and Garner in the past 6 years, they're the most general results of that nature to appear in the literature thus far, but neither of them subsume the other. So we wondered, so can both of these equivalences and also the aforementioned structure-semantics adjunctions from the first slide be captured by a common framework that also yields hopefully some new examples as well. So that's what the objective of this research is. So we basically have developed a general framework for studying enriched structure semantics adjunctions and monad theory equivalences relative to a subcategory of arities, which specializes to recover the aforementioned results and also yields some substantial new examples as well. So more specifically, and I'll define, I think, all of these terms, but given a subcategory of arities in a V category C over a symmetric monoidal closed category V, we will give some hypotheses, some kind of axiomatic hypotheses on these data that will give us a structure semantics adjunction, a monad theory equivalence, a quite rich theory of presentations for monads and theories, and even some more things too that I will briefly mention. Okay, so I'll just start by defining the basic concepts that we will be talking about. So the kind of the most fundamental concept is a subcategory of arities. So that's just a full sub V category that is dense in the enriched sense in a V category C over a symmetric monoidal closed category V. So it's just a full and dense sub V category that we do not require to be small. So it could be a large V category. In particular, it could be the entire V category C, which is not small in general.
Why is this not a generalization of Lawvere? I mean, if C is set, and so isn't it like a multi-sorted thing?
So this does generalize Lawvere's context. Yeah. So because so for Lawvere's context, we would take V and C to be set, and then J would be the full subcategory of set on the natural numbers, basically. So you take, so you take just the natural numbers and all functions between them, and that is the kind of Lawverian subcategory of arities.
Okay, I mean, but you can have more than just the natural numbers. You can have multi-sorted, so then you would have any category with products would probably work.
Yeah, exactly. Basically, So that is, So for example, like if you take, so V is set, you can also take C to be like a power of set. So like set to the X for some set X. And then you can take like a subcategory of arities in there, and that would give you like multi-sorted theories, or it should,
Right, okay, good.
Yeah, so just a kind of a technical thing, but so we don't assume that J is small or that V is complete or co-complete. We just assume that it has equalizers actually. But in most of our applications, it will be complete and co-complete, but we don't assume that in general. So we just have to work with a so-called universe extension, V prime. So it's just, it's a symmetric monoidal closed category into which V embeds by a strict symmetric monoidal inclusion. And V prime is just, it's a category defined over a larger universe of sets, but so it's just kind of a technical what's it called, a technical kind of convenience or tool. Okay, so the fact that J is a dense sub B category means that we have a fully faithful V prime functor. So N sub J, so remember J is the name of this inclusion, going from C to this pre-sheaf V prime category on J op. So it sends each object C of script C to this pre-sheaf. So just homming into C from the subcategory of Aries J. And we call this the J nerve V prime functor. And the fact that J is dense is equivalent to this V prime functor being fully faithful. And so the pre-sheaves in its essential image we call J-nerves. This is seems to be terminology that John Bourke and Richard Garner used in their papers. We just adopted that. Okay. So now we have this notion of a J pretheory. Now this was defined or considered by Linton and also Deers, but not under this name. I think Linton called them clones and Deers called them theories, which is kind of confusing. But then Bourke and Garner introduced this terminology of pretheory that we again adopted for our work. So it's just an identity on objects V-functor tau from J op to some V category T. So T has the same objects as J. And a J theory is a J pretheory T with a further property, namely that each of these V-functors or pre-sheaves is a J nerve. So if you fix, or so if you take any object J and then you post-compose with tau, then that pre-sheaf has to be a J nerve. So for certain choices of the subcategory of arities J, you recover more well-known notions of enriched or non-enriched algebraic theories. So for example, with J as the subcategory of arities on the natural numbers and C and V being set, J theories are exactly ordinary Lawvere theories. And for other choices of J, you can recover other known notions of enriched algebraic theory. Okay. So we have a category of J pretheories and its full subcategory of J theories. So the morphisms are just identity on objects V-functors between the pretheories that commute with the incoming functors from J op. Okay, so now we want to define algebras for J pretheories. So we let T be a J pretheory. We define its V prime category T alg of concrete T algebras, or just T algebras, as a pullback of V prime categories. So here we have the J nerve V prime functor below. We have precomposing with tau on the right, and we take the pullback of those two to get T alg. So it comes equipped with a forgetful V prime functor UT from T alg to C. So concretely, a T algebra is it's an object of C equipped with a V functor from T to V, such that when you precompose it with tau, you get the J nerve corresponding to the given object of C. So it's a bit abstract, but the point is that in kind of all the applications historically and that you care about, this T alg is kind of the standard notion of algebra. So in particular, in the Lawverian context where J is the natural numbers and C and V are set, and T is a Lawvere theory, then you recover, then this is just this is isomorphic to the usual category of algebras for a Lawvere theory. Okay. So now we're going to impose or discuss certain axioms on the subcategory of arities that will enable our results to work. So just first, we say that a J pretheory T is admissible if its V prime category T alg of algebras is actually a V category. It's just a kind of a technical condition, but and more importantly, if the forgetful V functor from T alg to C has a left adjoint. So basically, in kind of a short slogan, so T is admissible if T admits free algebras. So that's kind of the inspiration for the term admissible, is that it admits free algebras. So then we say that the subcategory of arities J that we're working with is amenable if every J theory is admissible, so or has free algebras. And we say that it is strongly amenable if it satisfies the stronger condition of every J pretheory T being admissible or admitting a free algebras. So we have these concepts of amenability and strong amenability for subcategories of arities. And I'll show, I'll show later on in the talk that almost all of the examples that we know of, as well as lots of new examples of subcategories of arities, are amenable and even strongly amenable. Okay. So now I basically have now discussed the semantic side of things, as I'll get back to shortly. But now I want to discuss the structure side. Or sorry. Okay. So now I want to discuss the structure side of things a bit. Okay. So we're going to define a notion of kind of tractable V category over C, but relative to the subcategory of arities J. So a J tractable V category over C is a V category over C. So that's just a V functor G going from some V category A down to C, such that a certain condition is satisfied, namely that C admits a certain weighted limit in the sense of an enriched category theory. So it admits this weighted limit where the weight is this presheaf and the diagram is G. So it's just kind of a condition to ensure that this V category over C is not too large in some sense, or it is well behaved in a certain sense relative to J. So then we have the full subcategory of V cat over C, the slice category over C, consisting of the J tractable V categories over C. And we write that as J tract of C. Okay, and now we also have the full subcategory of J pretheories, consisting of the admissible J pretheories, so the ones that admit free algebras. And now we define a semantics functor, sem, going from the opposite of this category, so the opposite of the category of admissible J pretheories, to the category of J tractable V categories over C. So this sends an admissible J pretheory T to its forgetful T algebra V functor. So this is a J tractable V category over C because UT has a left adjoint because T is admissible, and it's an easy fact that any V functor G having a left adjoint is J tractable. So in particular, UT is J tractable when T is admissible. So we have this semantics functor, and we now want to see if it has a left adjoint, which will be the J structure functor. Okay, so given a J tractable V category G from A to C over C, we can define a J theory based on G, so called the J structure of G. So it's going to be tau sub G from J op to a V category called structure of G. So to define this J theory, we basically factor a certain V prime functor. So we have J op going from J op to C op. Then we take the nerve V prime functor of G op, which ends up going from C op to this presheaf V prime category. So we take the identity on objects, fully faithful factorization of this composite. And so the first component, tau G, is identity on objects. So it's a J pretheory. And because G is J tractable by hypothesis, this does end up being a V category and a J theory. And so this is what we call the J structure of the J tractable V category G from A to C. Okay, so now we can present a structure semantics adjunction. So just one more definition. So a J algebraic V category over C is a V category over C that's in the essential image of the semantics functor. So it's isomorphic to the V category of algebras for some admissible J pretheory. And then we just let J algebra C be the full subcategory of J tractive C, consisting of these J algebraic V categories over C. And so now we have our first theorem. So if we have an amenable subcategory of arities, that's the weaker of the two potential hypotheses on J that we discussed. So then the semantics functor sem from admissible J pretheories op to J tractable V categories over C as a left adjoint structure that sends each J tractable V category over C to its J structure. And this is an idempotent adjunction, and it restricts to an adjoint equivalence between the full subcategory of J theories op and the full subcategory of J algebraic V categories over C. So the point is that if J is an amenable subcategory of arities, then we get a certain J relative structure semantics adjunction. And again, for certain choices of J, this specializes to give all of the structure semantics adjunctions that I mentioned at the beginning of the talk, but I'll come back to that later as well. Okay. Okay, so there's kind of a nice consequence of this.
One quick question. Does these back up? This adjunction is an enriched injunction, right?
So this one is not enriched because so here we have just ordinary categories on both sides. So these are not V categories; they're just ordinary categories. So we have the ordinary category of J theories and the ordinary category of J algebraic V categories over C.
Okay.
Yeah. So just an adjunction in the ordinary sense. Yeah.
All right. Okay. Never mind.
Okay. So Bourke and Garner, in their paper that I mentioned, in their context, they obtained a monad-pretheory adjunction. Now their context was with a locally presentable V category C over a locally presentable closed category V. Our context is much more general, but we can still do a similar thing. So given an admissible J pretheory T, its forgetful T algebra V-functor is actually strictly monadic. That's not too hard to show. And hence the semantics functor sem co-restricts to the full subcategory of the strictly monadic V categories over C. And okay, so if J is amenable, then because it's pretty well known that the category of strictly monadic V categories over C is dually equivalent to the category of V monads on C. I believe this is due to Dubuc. So given this dual equivalence, the structure semantics adjunction of the previous theorem, which exists because J is amenable, gives us an idempotent adjunction between admissible J pretheories on the one side and arbitrary V monads on the other side. So what this adjunction does is the right adjoint phi sends a V monad T to its so-called Kleisli J theory. So basically, that is essentially the J theory whose objects are the free T algebras on objects of J, roughly speaking. And then the left adjoint psi sends an admissible J pretheory T to its free algebra V monad. because T is admissible. So it has free algebras, and hence we can take its free T algebra V monad. Okay, so we get this monad, this adjunction between admissible J pretheories and arbitrary V monads on C. Okay, so another, I think this is the last definition, I hope. Yeah, so a V monad, so we want to talk about or we will get a certain monad theory equivalence, but we first have to define what monads will be equivalent to J theories. So these are the J nervous V monads. Again, this terminology is due to Bourke and Garner in their recent paper, which we just adopted this term for our work. So a V monad T on C is said to be J nervous if T is isomorphic to the free T algebra V monad for some admissible J pretheory T. Now, there's also a more technical definition that does not involve pretheories, but just to keep things somewhat or more simple than they could have been, we just chose to use this equivalent definition for this talk. Okay, so these are the monads that we will be interested in because they form one side of a monad theory equivalence. So if we have an amenable subcategory,
why do they call them nervous?
Oh yeah. So good question. Yeah. Yeah. So it's a bit of a strange sounding term, somewhat. Basically, I think they are called J nervous because so this more technical definition is the definition that they originally gave, and it's expressed in terms of J nerves. So basically T satisfies this more technical definition if certain conditions involving J nerves are satisfied. So I think that's what inspired the term J nervous for them. Yeah, it's potentially a bit kind of weird sounding, but we chose to adopt it for this specific paper. But yeah, so I think that's the origin. Okay, so if J, so again, we are supposing that J is an amenable subcategory of arities. So then the idempotent monad-pretheory adjunction that I recently mentioned, it restricts to an adjoint equivalence between J theories and J nervous V monads. And this equivalence commutes with semantics in an appropriate sense. So roughly speaking, the V category of algebras for a J theory is isomorphic to the V category of algebras for the corresponding J nervous V monad, and conversely. But yeah, but the point is that if J is an amenable subcategory of arities, then we automatically get a monad theory equivalence between J theories and these J nervous V monads. So just a certain full subcategory of the V monads. Also, the full subcategory of J theories is reflective in the category of admissible J pretheories, and the full subcategory of J nervous V monads is co-reflective in the category of all V monads. So these are consequences of the idempotence of this monad pretheory adjunction up here. Okay, so that is kind of the I guess one of the main theorems that we have. Now I'm going to somewhat briefly discuss some additional nice results that we get if the subcategory of arities is strongly amenable. So up until now, we've only been supposing that J is amenable, which is the weaker of the two hypotheses that we can put on J. So along with supposing that J is small and strongly amenable, we also suppose that V is complete and co-complete from now on, and that C is a co-complete and co-tensored V category. And so one thing that we can prove under these slightly stronger assumptions is that the categories of J pretheories, J theories, and J nervous V monads are all co-complete. And small co-limits in these categories are sent to limits in this slice category V cat over C by the respective canonical semantics functors. So basically, these co-limits are called algebraic because they are sent to limits by the semantics functors. So essentially, these categories all have well-behaved co-limits under these extra assumptions. Okay. Now we also have some nice results about signatures and presentations under these extra hypotheses. So a J signature is a V functor sigma from ob J to C, where ob J is the discrete V category on the objects of J. So it's just an ob J indexed family of objects of C, nothing more than that. And we have a category of J signatures, sig J of C, and a forgetful functor U from J nervous V monads on C to J signatures that sends a J nervous V monad T to the family of all the objects Tj for J ranging over the objects of J. And so this functor is monadic. And as a consequence, every J nervous V monad has a J presentation in a certain sense. So basically, this technically means that, or it basically means that every J nervous V monad has a presentation in terms of a certain kind of abstract notion of equations. Yeah. And then kind of as a converse result, every J presentation in a certain sense actually presents a J nervous V monad TP, whose V category of algebras is isomorphic to the V category of algebras of the presentation in a certain sense. So basically, we have just a very well-behaved theory of presentations for J nervous V monads when J is small and strongly amenable, and V and C are basically complete and co-complete. Okay, just some other brief, nice consequences. So if we also suppose that T-alg has conical reflexive co-equalizers for every J pretheory T, then we get some even nicer consequences. So one of them is that if you have a morphism H of J pretheories, then the corresponding so-called algebraic V functor, which is just sem of H from U-alg to T-alg, is strictly monadic. So it has a left adjoint in particular. And also, if you have a J pretheory T, then the full sub V category of T algebras so this is a full sub V category of V functors from T to V, and this is a reflective sub V category. Okay, so those are kind of all of the main results that I'll be discussing, I believe. So now I want to conclude the talk with some examples. So yes, I've discussed subcategories of arities, and so if the subcategory of arities J is amenable, then we get several results, including a structure-semantics adjunction and a monad-pretheory equivalence. If it is strongly amenable, then we get certain additional nice results. So now I'll give some examples of amenable and strongly amenable subcategories of arities. So the first example is one where I will define that strange looking eleutheric term. So, okay, so a subcategory of arities J is eleutheric if every V functor H from J to C has a left con-extension along J that is also preserved by Halming out of each object of J in the enriched sense. so it's a bit technical sounding, but this is actually quite this has quite a rich class of examples. So for example, if you take a locally alpha presentable V category C over a locally alpha presentable closed category V, then the full sub V category of enriched alpha presentable objects of C is eleutheric. If you take a complete and co-complete Cartesian closed category V, then you can consider the so-called strongly finitary subcategory of arities SF of V in V, which it just consists of the finite copowers of the terminal object. So this can essentially be regarded as the subcategory of arities in V consisting of the natural numbers. So basically this subcategory of arities essentially generalizes the natural numbers in set to any complete and co-complete Cartesian closed V. So in any symmetric middle closed category V, if you just take the unit object, that is an eleutheric subcategory of arities. In any V category C, the identity, like the whole V category C is an eleutheric subcategory of arities. Of course, not in general small, because C will in general be a large V category. If V is complete, then we can consider the Yoneda embedding for any small V category A. This is an eleutheric subcategory of arities. And if V is complete and co-complete, then any free psi co-completion C of J, of a small V category J under a class of small weights psi in the sense of enriched category theory is an eleutheric subcategory of arities. So we have a wide number of examples of eleutheric subcategories of arities. And the main point of this example is that we have this theorem. So, so any eleutheric subcategory of arities is amenable. So hence we get hence we get all of the main results, structure-semantics adjunction, the monad-pretheory adjunction, and the monad-theory equivalence. We'll also observe very shortly that most of the examples I just gave of eleutheric subcategories of arities are also bounded in a certain sense, and that also makes them strongly amenable. So we get even further nice results for most of those subcategories of arities. So if J is just the whole closed category V, so here C is equal to V, and J is the identity V-functor on V, and then this is an eleutheric and large, well, in general, large subcategory of arities. Then we recover Dubuc's structure-semantics adjunction and his monad theory equivalence as well, which I didn't mention yet, but he also proved a monad theory equivalence, which we recover by making this choice of J and C.
But in the beginning, you said something about that Dubuc's theories weren't a generalization of Lawvere's. So,
yeah. So yes, that's right. So yeah, so we also recover Lawvere's results too. If we take J or so, if we take V and C to be set and J to be the natural numbers. So then by making that choice of J, C, and V, we recover Lawvere's structure-semantics adjunction and monad theory equivalence as well. But Dubuc's.
Can you give like a 2-minute or 1-minute explanation? What does Dubuc's theories look like?
Yeah, sure. So okay. So for example, if we take V to be set, then Dubuc's V theories, when V is set, are basically like, they're like large Lawvere theories that also Linton considered. So basically the arities are arbitrary sets. So the arities are not just natural numbers. You can have, so the arities are arbitrary sets. So a V theory in this context is a category whose objects are all sets, and you have an identity on objects functor from set into this category. So basically it's like a large Lawvere theory, essentially, where the arities can be arbitrary sets and not just natural numbers.
Perfect, thank you.
Yeah, sure. Okay, so, right, and then, so if we take C to be V and J to be an eleutheric system of arities, which means that J contains the unit object I and is closed under the monoidal product, then we recover Lucyshyn-Wright's equivalence between J theories and J array V monads on V, because in this context of J being eleutheric, J nervous V monads are precisely J array V monads, where J array means basically that the monad preserves certain J relative colimits. So they're, yeah, but I won't dwell too much. Okay. Okay, so now on to the second example. So first, for this example, we'll make just some background assumptions. So V is complete and co-complete and has an enriched factorization system in the sense of this paper by Lucyshyn-Wright. So then C, we assume is co-complete and co-tensored. It has a compatible enriched factorization system, EC-MC. So compatible means that homming out of every object of C sends MC morphisms to M morphisms. It's just a technically convenient assumption, which is not very strong. And also we assume that C has arbitrary co-intersections of EC morphisms. So it has like arbitrary, even large, wide pushouts of morphisms in the left class EC with the same domain. So this is in particular true if C is co-well powered, for example. Okay, yeah, and then also assume that EC-MC is a proper factorization system, or that C is co-well powered with respect to EC, which means that every object has just a set or a small set of outgoing morphisms in the left class EC. Okay, just some somewhat technical assumptions, but they are needed to make this definition, which seems a bit circular, but we say, so a small subcategory of arities is bounded if each object of J is bounded. So yeah, not very informative and sounds circular, but the point is that J, so an object of J being bounded has a precise definition. It's basically like a factorization system theoretic variant of the notion of being presentable, or sometimes called compact. So it's a factorization system theoretic variant of preserving suitably filtered colimits. But it's not quite that, but it's related. And this is defined explicitly in my paper with Lucyshyn-Wright 12 cited here. Now, so again, the point is that this is not a very strong condition. It's quite widely satisfied. For example, so if C is a locally bounded V category in the sense of another paper of mine with Lucyshyn-Wright over a locally bounded closed category V, then any small subcategory of arities J in C is automatically bounded. But the point is that J being bounded is not a very strong condition. It it is satisfied in lots of examples. Okay, so the point of all that was this theorem. So if J is a small subcategory of arities that happens to be contained in a bounded and eleutheric subcategory of arities, so J in particular could be bounded and eleutheric itself, then J is strongly amenable, and also T-alg has small conical colimits, and hence in particular conical reflexive coequalizers for every J pretheory T. So we also get those extra nice results because of this last part here. So for example, most of the above examples of eleutheric subcategories of arities are also bounded and hence strongly amenable. Any small subcategory of arities in a locally presentable V category C over a locally presentable closed category V happens to be contained in a bounded and eleutheric subcategory of arities. And this allows us to recover some of the main results of that John Bourke and Richard Garner paper. Because, for example, their monad-pretheory adjunction and monad-theory equivalence. And also, if we drop the requirement of being eleutheric, but we strengthen the notion of being bounded in certain ways, we can also get other examples of strongly amenable subcategories of arities, but I won't go into that, but it will be in one of the papers based on this work. Okay. Now the final quite new example is in the locally bounded context. So just a first quick definition. So a V category C we say is V sketchable if C is equivalent to the V category of models of a small phi theory T for a class of small weights phi. So this is a somewhat technical definition, but basically it means that C is equivalent to a V category of algebras for some kind of enriched theory. Now, the main result that we have here is that, so let J be any small subcategory of arities in a V sketchable V category C over a locally bounded closed category V. So I'll give examples of locally bounded closed categories in the next slide. So in this context, J is always strongly amenable. Also, if V is co-well powered in a certain sense, then T-alg is a locally bounded V category, and hence it's in particular co-complete for any J pretheory T. And also T-alg is a locally bounded V category for any J nervous V monad T. So basically we get some very, very nice properties of V categories of algebras for J pretheories and J nervous V monads in this context. Now, this also gives us a second method for recovering some of Bourke and Garner's main results, because every locally presentable closed category V is locally bounded, and every locally presentable V category is V sketchable. So hence their main results can be obtained by applying this. Okay, so now V itself is V sketchable, as is quite easy to show. So we can take C to be V itself and obtain the following consequence. So let J be any small subcategory of arities in a locally bounded closed category V. So then J is strongly amenable, and T-alg is co-complete for every J pretheory T. So hence it has conical reflexive coequalizers. So we get those extra nice results as well. Okay, so here, so there are lots and lots of examples of locally bounded closed categories. This is an extremely general result. It seems like actually most, I I think it's fair to say that most symmetric monadal closed categories in nature are locally bounded, but that's possibly too strong of a statement, but tons and tons of them are. So for example, any locally presentable closed category, any co-complete locally Cartesian closed category with a small generator. So this includes, for example, Dubuc's concrete quasi-topuses and the convenient categories of smooth spaces studied in differential geometry that were discussed by John Baez and Alexander Hoffnung in this paper here. Any symmetric monadal closed topological category over set is a locally bounded closed category. In particular, many convenient Cartesian closed categories of topological spaces are locally bounded closed categories. So we get lots and lots of examples of locally bounded closed categories, including many that are not locally presentable. And in any such closed category V, any small subcategory of arities is strongly amenable. Okay. So now I will start to wrap up. So we have developed a general framework for enriched structure semantics adjunctions and monad theory equivalences for subcategories of arities. So if J is amenable, meaning basically that every J theory has free algebras, then we get a structure semantics adjunction between admissible J pretheories and J tractable V categories over C, and a monad theory equivalence between J theories and J nervous V monads. If C and V are basically complete and co-complete, then J is small and strongly amenable, so that every J pretheory has free algebras. And we also get some other nice results, namely a monad-pretheory adjunction between arbitrary V monads and arbitrary J pretheories, and a rich theory of presentations and algebraic co-limits for J theories and J nervous V monads, and more as well. So many of the previously studied subcategories of arities in the literature are amenable or even strongly amenable, and therefore we recover as special cases many of the enriched structure semantics adjunctions and monad theory equivalences established in the literature. For example, those of Lawvere, Linton, Dubuc, John Power, Lucyshyn-Wright, and John Bourke and Richard Garner. So one of our main new examples is that every small subcategory of arities in a V sketchable V category C over a locally bounded closed category V is strongly amenable. So we can take C to be V itself because V is V sketchable. And as a result, so examples of locally bounded closed categories include all locally presentable closed categories and many convenient categories of topological spaces and smooth spaces, which are not locally presentable in general. So I think that is it. Yeah, so thank you very much for listening. I hope it was sufficiently clear.
It was very clear. Thank you. It was very interesting.
Thank you.
Any questions?
Oops.
I have a quick question. Is there any relationship with operad theory? In other words, you can make a lot of generalizations of operads too.
Yes. Yeah, that's a good question. So we haven't studied that in really at all, but like there certainly is a connection for sure. I just haven't really looked at it in much depth myself, but there are papers that I've read that do cover, like, I guess, operads and algebraic theories that are relevant. So like, for example, there's this paper by Berger, Melies, and Weber. I think it's called Monads and Theories and their Associated Arities or something. And there they talk about operas, I believe. But yeah, but we haven't really studied that in this context. But yeah, but it's an interesting, I guess, prospect. So yeah, I'll think about it some more.
And you'll think about it and you'll come back and give us a lecture on it.
Yeah, sure.
Okay. Any other questions? Okay, thank you very much. I just want to say next week we're having Alex Martuskovsky, whatever. Sorry, I don't know can't pronounce his name. And he's going to give the first of a two-part, not him and a student of his. And his talk is going to be a reflector in search of a category. Anyways, so thank you very much, Jason. And
thanks again.
Baruch says hello.
Bye.
Okay.